Voyager 2 saw Uranus for only a few hours in 1986. The question is why that brief flyby is still almost everything we know up close about an entire planet. Uranus is not a small target. It becomes a giant world with rings, moons, storms, seasons, and a magnetic field that does not behave like the neat textbook version. It's close enough to be part of the solar system we claim to know, but distant enough that returning there has remained easy to postpone. That's the contradiction. Uranus is scientifically rich, but operationally neglected. The problem is not that nobody cares. The problem is distance, timing, cost, power, launch windows, and the long patience a real outer planet mission demands. We are going to work through Uranus as a real exploration problem, from the one brief flyby to the mission architecture that still has not returned. This question needs a careful path, so we are going to work through it properly. By the end of this video, you will understand why Uranus remains almost unexplored, and why the next mission is not just overdue, but scientifically different from the first. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Now, start with the spacecraft itself. Voyager 2 did not drift past Uranus as a side note. It made a real encounter on January 24, 1986, and for the first time a machine built on Earth looked at that blue-green world from close range. That matters because it is still the foundation of nearly everything we say about Uranus up close. But the encounter was brief. Voyager passed about 81,500 kilometers from the cloud tops, close enough to change planetary science, yet moving too quickly to settle the system. NASA describes only about 5.5 hours of close study for an entire major planet that is not a visit in the ordinary sense. It becomes a narrow window. And here is the first correction. Uranus has not been ignored by science. It has been limited by the kind of access we have had. One fast flyby can discover rings, moons, winds, magnetic surprises. It cannot sit in the system and watch how those pieces behave over time. Think about what an orbiter changes. It does not only take more pictures, it keeps returning to different longitudes and latitudes. It measures gravity through repeated passes. It traces a magnetic field as the planet rotates. It compares the rings after days, months, and years. It turns a glimpse into a pattern. Voyager was never that kind of mission. It was part of the great outer planet tour, a spacecraft built to keep moving. Uranus was one destination in a path that also had to preserve the chance of reaching Neptune. The spacecraft could not break. It could not circle back. It could not choose Uranus over the rest of the route. So when we say Uranus is almost unexplored, we need to hear the phrase carefully. Almost unexplored does not mean untouched. It means almost unexplored locally, slowly, and repeatedly. It means the only close spacecraft dataset comes from a mission that had to leave almost as soon as it arrived. Look at the human shape of that. We have a planet 4 times wider than Earth, wrapped in an atmosphere carrying rings and moons, turning almost sideways in the dark. Our close record of it is built around one afternoon in 1986. That contrast is the whole doorway into the story. But we should not turn the doorway into blame. The easiest version says nobody cared enough. The better version is more interesting. Uranus asks for a mission that is slow, heavy, powered for deep space, able to survive the cold, able to arrive with enough fuel or design margin to stop. That becomes a very different thing from flying by. Now notice the trap in the word visited. We visit a city by staying there. A spacecraft can visit a planet by crossing its neighborhood at tens of thousands of kilometers per hour. The same word hides 2 very different acts. Voyager entered the Uranian system, measured what it could, and then vanished down the path to Neptune. And yet the flyby was not small. It returned more than 7,000 photographs. It found new rings and moons. It revealed a magnetic field tilted far from the rotation axis and offset from the center. It showed that the quiet, visible disk was not the same as a simple planet. So that is why the story has tension. Voyager was good enough to prove Uranus deserved more attention. It was not designed to give that attention itself. A successful reconnaissance can deepen the mystery because it shows exactly where the first map ends. Picture a coastline seen from an aircraft through gaps in cloud. You can mark the cliffs, you can see islands, you can even spot a strange river mouth. You cannot claim to know the interior. Uranus is like that, except the coastline is a whole planetary system, and the aircraft has never come back. So the first answer is simple, but not shallow. Uranus remains almost unexplored because the only spacecraft that reached it was a flyby spacecraft. It opened the subject, it did not complete it. The next questions all follow from that boundary. We need a dedicated orbiter and atmospheric probe because the missing measurements are not cosmetic. They are the measurements that turn scattered facts into a working planet. Deep composition, noble gases, gravity, magnetism, seasonal behavior, ring dynamics, moon geology, and long-term change. And that is where the documentary begins to widen. The problem is not just why a spacecraft has not gone back. The problem is why going back properly is so hard that the solar system still contains a major planet known mostly from a single close pass. Now we can leave the first correction behind. Voyager counted, Voyager mattered, and Voyager changed the subject forever. The encounter was shaped by geometry, time, and escape. The next layer is the path itself, because the way Voyager saw Uranus explains why even its best data came with shadows built in. Now hold that boundary in mind, because it changes the scale of every fact that follows. 5.5 hours is shorter than a normal workday. In that span, Voyager had to point instruments, store data, keep its antenna plan alive, and prepare for the next leg of a journey that could not be repeated. A whole planetary system had to fit through that moving slit of time. But exploration is not only the moment of closest approach, it becomes the ability to ask a question, see an answer, and then adjust the next question. At Mars, Jupiter, and Saturn, orbiters changed the story because they could react, they could find a storm and watch it, they could see a moon with strange terrain and come back from another angle, they could trade one plan for a better one after the planet surprised them. Voyager could not do that at Uranus. If a camera frame showed a puzzling boundary on Miranda, the spacecraft could not schedule another close pass 2 weeks later. If the magnetic field looked stranger than expected, it could not move into a different orbit and sample another local time. If a ring edge hinted at shepherding moons, the flyby could not pause to map the faint dust around it. So that is why the word reconnaissance is so useful. Reconnaissance is real, it's brave, valuable, and often decisive. It tells you where the mountains are. It tells you whether the coast is safe. It may reveal something nobody knew existed. But reconnaissance is the beginning of a campaign, not the campaign itself. And Uranus never received the next step. No spacecraft settled into orbit. No probe descended under the clouds. No close-range mission returned when the northern hemispheres came into better light. The first spacecraft record became the only spacecraft record, and that accident of history shaped the planet's reputation. We can feel the distortion in ordinary pictures. Uranus often appears as a smooth blue ball, almost featureless, as if nature forgot to finish painting it. But that image is partly an observing circumstance. A quiet face during one season does not prove a quiet planet. A low-contrast photograph under weak sunlight does not prove a simple atmosphere. A short encounter does not prove there was nothing else to see. So the question becomes sharper. We are not asking why nobody has ever cared about a distant blue world. The scientific community has cared for decades. We are asking why the second act never came. Why did the first close look remain alone while other planets accumulated orbiters, landers, rovers, and long campaigns? The answer starts with the spacecraft path, but it does not end there. It will move through light, seasons, fields, heat, moons, launch geometry, power, propellant, and priority. Each layer makes the original contradiction less mysterious and more serious. Uranus is not empty because the story is thin. Uranus is thin in our records because the proper story has been so hard to begin. Now slow the calendar down around that afternoon. Before closest approach, Voyager had been watching from far away, sharpening a point of light into a planet. After closest approach, it kept sending back what it had captured. But the close physical encounter, the part where distance finally stopped being an abstraction, was measured in hours. We can almost feel the unfairness of that. A world with an 84-year orbit gave humanity one work shift of local access. And local access is the expensive part. From Earth we can keep looking. Telescopes can track bright clouds and seasonal changes. They can improve maps and measure light in wavelengths Voyager could not use in the same way. But they still look across billions of kilometers. They do not feel the gravity field tugging directly on a spacecraft. They do not carry a probe below the haze. They do not pass through the plasma environment while the planet turns beneath them. So when we compare Uranus with better explored worlds, we should compare methods, not just names. Mars has had orbiters, landers, rovers, repeated campaigns, a steady pipeline of corrected guesses. Jupiter has had Galileo and Juno. Saturn had Cassini. Those missions did not simply add more photographs. They changed the scientific posture from one encounter to continuing interrogation. Uranus never crossed that threshold. We still build many of our local questions from Voyager's first cut through the system, then extend them with distant observing and models. That can produce good science, it already has, but it leaves a special kind of uncertainty, because the missing thing is not one measurement. The missing thing is residence, and residence changes the tone of exploration. A resident spacecraft can notice what it did not expect, then spend the next orbit testing it. A flyby can only hand scientists a treasure chest after the ship has already gone over the horizon. Voyager's treasure chest was rich, the horizon still closed behind it. Now imagine arriving at a planet that is lying almost on its side. Uranus does not present itself like Jupiter or Saturn, with equatorial belts stretched neatly across the view. Its rotation axis is tipped close to the plane of its orbit. During the Voyager encounter, that tilt turned the system into something like a target pointed toward the spacecraft. NASA's historical account describes the geometry as a bullseye. The planet sat near the center, with rings and moons arranged around it from Voyager's perspective. That sounds elegant, but it created a sampling problem. A beautiful geometry for one image can be a poor geometry for complete exploration. But the bigger issue was season. Uranus was near southern summer solstice. One side of the system had sunlight. The opposite hemispheres of the planet and moons were largely hidden from visible light study. Voyager did not choose a balanced survey. It arrived when nature offered one tilted seasonal face, so a moon photographed by Voyager was not simply photographed. It was photographed from one path, under one lighting condition, at one phase in an 84-year Uranian year. That's not a small caveat. It decides what terrain can be seen, what shadows reveal, and what entire hemispheres remain undersampled, and the light itself was weak. NASA science describes the sunlight at Uranus as roughly 400 times fainter than at Earth. NASA history compares it with Saturn and still finds a major drop. The spacecraft needed long exposures and careful image-motion compensation. At that distance, even taking a clear picture becomes an engineering event. Think about that for a second. Uranus was not only far away, it was dim. The spacecraft was moving. The encounter was brief. The system was tilted. The northern hemispheres were largely unavailable. Each limit by itself would matter. Together they define the shape of the record we inherited. Now add the Neptune constraint. Voyager's Uranus path had to preserve the future flyby of Neptune. That does not make Uranus an afterthought. It makes the encounter part of a larger celestial choreography. The path that let Voyager reach one more planet was not the path a dedicated Uranus scientist would design from scratch. This becomes where the word exploration starts to stretch. A flyby must accept the route. An orbiter can build a campaign. A flyby takes the light as it finds it. An orbiter waits for geometry to change. A flyby uses a single crossing. An orbiter turns crossings into a map. And because Uranus rotates on its side, time matters more than our intuition expects. The planet's seasons are extreme. Poles can experience decades of sunlight or darkness. A snapshot near solstice tells us something real, but it cannot tell us how the planet behaves across its long seasonal swing. Remote telescopes help here. Hubble, ground-based observatories, and Webb-era measurements extend the story beyond 1986. They show that Uranus is not frozen in the Voyager image. Clouds change, upper atmosphere features appear, the seasonal context shifts. That remote timeline is valuable. But remote watching is not the same as local measurement. A telescope can see reflected light and emissions. It cannot descend through the atmosphere with instruments. It cannot taste noble gases. It cannot map the gravity field from orbit. It cannot fly close to each major moon again and again under changing illumination. So the geometry trap is not only a Voyager problem, it becomes a lesson in what planetary knowledge costs. If a world rotates strangely, moves slowly around the sun, and sits in faint light, one encounter does not average out the conditions, it freezes them into the archive. Look at the psychological effect. Voyager images gave Uranus a face. Once a world has a face, it feels known. But the face was partly a product of the encounter. Bland visible clouds under that lighting did not mean a simple atmosphere. Limited moon coverage did not mean simple moons. A sparse ring view did not mean a finished ring system. And this is why the title question survives the first objection. Yes, Voyager went there. It went there through a particular keyhole. It looked through that keyhole precisely, then the keyhole closed. For almost 4 decades, no spacecraft has opened another one. Now the next turn is important. A limited view can still discover extraordinary things. Voyager did. It found enough to make Uranus stranger, not simpler. The geometry narrowed the evidence, but the evidence it captured was full of reasons to go back. Now picture the difference between seeing a globe from one doorway and walking around it. From the doorway, the object is real, its color is real, its outline is real. But the far side may as well be another world. At Uranus, the doorway was not only narrow, it was tilted by the planet itself. Uranus's sideways rotation is often treated like a trivia fact, but for exploration it is a practical obstacle. The orientation decides where sunlight falls, which moon faces are visible, and how the rings cut across a camera frame. The planet's odd posture turns time into a scientific instrument. If you want a balanced view, you cannot simply point better. You have to wait through seasons that last for decades. Voyager arrived near one of those seasonal extremes. That made the southern regions easier to see and the northern regions much harder to examine in visible light. On Earth, a winter hemisphere returns in months. At Uranus, the seasonal clock is so slow that a human career can pass while the geometry is still changing. A spacecraft that only passes once inherits that slow clock without being able to use it. And the rings complicate the view. Uranus's rings are dark and narrow compared with Saturn's bright architecture. Seeing them well depends on angle, illumination, and sensitivity. A single flyby can discover structure, but it cannot build a full ring weather report. It cannot watch small moons tug on ring edges over many orbits. It cannot separate a stable pattern from a temporary alignment. The moons carry the same problem in stone and ice. A moon surface is read through light and shadow. Low sun can exaggerate relief. High sun can flatten it. Darkness can hide half the argument. Voyager gave us precious images of the major moons, yet many landscapes remained poorly mapped or unseen under different lighting. Here is where remote observing does important work. Telescopes from Earth and near Earth can watch Uranus through changing seasons. They can detect bright clouds, storms, thermal signatures, and upper atmosphere behavior. They extend the timeline beyond the single spacecraft encounter, and we should not dismiss that. Without that patient remote work, the Voyager image would be far more frozen in time. But telescopes do not remove the need for local exploration. Distance blurs small things. It limits the faintest ring material. It turns moon geology into hints. It cannot place a magnetometer inside the shifting field or a mass spectrometer inside the atmosphere. It cannot fly past Ariel 1 month and Titania the next with the same close instrument set. So the geometry trap is also a humility lesson. Sometimes the data we have is not wrong, it's just located in one corner of a much larger question. Voyager's angle was not a flaw in the mission, it was the unavoidable price of a flyby path through a sideways system. That price still shapes our imagination. The archive gives Uranus a certain face: calm, blue, distant, spare. A dedicated mission might find that the face changes with season, depth, and viewing angle. It might discover that what looked simple was a temporary surface expression of a deeper circulation. We do not know, because the path through the keyhole has not been repeated from inside the room. Now imagine trying to reconstruct a building from a single window at dusk. You might draw the room beautifully, you might measure the wall you can see, you might even catch a reflection of the hallway behind you, but the architecture remains partly guessed because the viewing position chose the evidence before you did. That's what the Uranian geometry did to Voyager. The spacecraft did not see a neutral, evenly lit system. It saw a system offered at a particular season, from a particular direction, while moving on a path that had to satisfy the larger grand tour. Every image carried that history inside it. Every missing hemisphere carried it too. And because Uranus moves so slowly around the Sun, the missing season is not easy to replace. On Earth, we can wait a year and see the cycle repeat. At Uranus, one full year is longer than most human lives. A pole can spend decades facing sunlight and decades turned away. If we want to know how the atmosphere, rings, and moons respond to that long swing, we need either generations of remote observing or a spacecraft patient enough to work inside the system while the season changes. We also need to remember the light. 400 times less sunlight than Earth is not just a poetic measure of distance. It affects exposure times, it affects instrument design, it affects how much solar power a future spacecraft can count on. The same dimness that made Voyager's pictures harder also hints at why a return mission cannot be built like an inner solar system probe. So geometry becomes the first doorway into engineering. The path shapes the science, the sunlight shapes the spacecraft, the season shapes the archive. Once we see that, the old phrase, "we already went there," starts to feel too small for the problem. Before we go deeper into Voyager's discoveries, let's hold the argument in one place. The story so far has shown that Uranus was not neglected because it lacked scientific value. It was constrained by a single fast flyby, a sideways seasonal geometry, weak light, and a route that had to preserve the Neptune encounter. So the next question is not whether Voyager mattered, it is what that brief, awkward view actually found, and why those findings made a return more necessary rather than less. Now give the flyby its full credit. Uranus did not disappoint because it looked calm. The apparent calm was part of the surprise. Voyager found a planet whose visible face was muted compared with Jupiter or Neptune, yet whose system was busy once the instruments looked beyond first impression. The spacecraft returned more than 7,000 photographs. It saw rings that were dark and narrow. It found new rings and new moons, with NASA sources differing slightly on the exact moon count depending on wording and later accounting. We do not need the counting dispute. The important point is that the Uranian system grew more complex during the encounter. But the planet itself resisted easy reading in visible light. Uranus looked smooth and almost blank. That could have supported the old lazy image of a boring blue world. Then the wind measurements and other data complicated the picture. A quiet face did not mean a quiet atmosphere. And the rings mattered too. Uranus's rings are not the grand, bright sheet of Saturn. They are dark, narrow, and difficult. Voyager found structure in a system that had first been detected through stellar occultations, the tiny dimming of a background star. That becomes a very Uranian kind of discovery. Subtle, indirect, and easy to underestimate. Now move outward to the moons. Voyager photographed the 5 large classical moons: Miranda, Ariel, Umbriel, Titania, and Oberon. Each one carried a different surface history. They were not interchangeable ice balls. They were small worlds with scars, cliffs, old terrain, hints of internal stories. Miranda became the visual shock. It looked patched together, with huge canyons and broken provinces that seemed too dramatic for a moon so small. Voyager could not explain that terrain completely. It could show the problem. It could not stay and build the full geologic history. So Voyager gave us exactly the kind of evidence that creates a hunger for more evidence. The images were real. The discoveries were historic. Every discovery arrived with a question attached. What shaped Miranda? How active were Ariel and the other moons? How did the rings hold their structure? And what was happening below the smooth atmosphere? Then came the magnetic field. Uranus did not carry a neat field aligned close to its rotation axis. Voyager measured a field tilted by roughly 55 to 59 degrees and offset from the planet's center. That's not just a weird statistic. It changes the whole environment around the planet. Think of a magnet stuck inside a spinning ball, but placed off-center and tilted sharply. Now tip the ball itself almost sideways as it travels around the sun. The result is a magnetosphere that should twist, wobble, and change in ways a single flyby can barely sample. And this is where the first half of the video pays off. Voyager was not inadequate because it failed. It was inadequate because it succeeded at reconnaissance. It uncovered a system too rich for reconnaissance alone. That becomes a very different story from saying the flyby was not useful. Look at how many future mission goals begin inside Voyager's discoveries. Rings require follow-up. Moons require repeat imaging and gravity context. The field requires long local sampling. The atmosphere requires vertical composition. The interior requires gravity and magnetic constraints. One encounter created a to-do list that only a very different mission could complete. Now we can feel why generic Uranus facts are not enough. Tilt, rings, moons, winds, and magnetism are not random trivia. They are evidence that the planet is a system of unresolved mechanisms. The correct question after each fact is not merely what happened. It's what measurement would decide between possible explanations. And we should be careful about the emotional tone. Uranus did not shout. It did not give Voyager a great storm on the face of the planet or a Saturn-like ring portrait. Its drama was quieter. A strange field, dark rings, small moons with broken surfaces. A cold giant hiding most of itself below a pale atmosphere. That quieter drama is exactly why the planet stayed underestimated. A world that does not look spectacular in one visible light encounter can still be scientifically urgent. Voyager's instruments told us that the surface-level image said calm, the deeper dataset said unresolved, so the next question becomes sharper. If the discoveries were so strong, why did the flyby not settle the biggest mysteries? The answer starts with the strangest Voyager result of all, a magnetic environment that refuses to behave like a simple, stable shell around the planet. Now we should give the flyby its full credit. The mistake is not respecting Voyager too much. The mistake is mistaking its achievement for completion. In a few hours near Uranus, one aging spacecraft turned a distant disk into a real place with weather, rings, moons, magnetic structure, geological surprises. The visible planet looked quiet, but the instruments told a more restless story. Winds were measured in an atmosphere that did not advertise itself with Jupiter-like belts. That becomes an important warning. Nature does not owe us obvious visual drama. A planet can hide motion under a smooth face, especially when the light is weak and the observing geometry is brief. Voyager also sharpened the ring story. Uranus's rings had been detected from Earth before the encounter, but close spacecraft observations gave them a physical presence. These were not grand golden bands like Saturn's. They were dark, narrow, and difficult, with structure that raised questions about small moons, confinement, particle sizes, evolution. A ring system like that is not a decoration. It becomes a laboratory for gravity and collision in miniature. Then there were the moons. Miranda became the famous shock, a small icy world with fractured, patched, almost assembled-looking terrain. But Miranda should not absorb all the attention. Ariel, Umbriel, Titania, and Oberon each carried pieces of a larger story about heat, impacts, resurfacing, and the quiet lives of icy satellites far from the Sun. And because Voyager could only see so much, the images became invitations. A cliff or groove on an icy moon is not an answer by itself. It becomes a clue about stress, heat, internal structure, and history. To turn that clue into a full explanation, scientists need global mapping, topography, repeat coverage, gravity constraints, comparisons across the system. The magnetic field discovery may have been even more disruptive. A field tilted far from the rotation axis and offset from the planet's center turns Uranus into a rotating electrical puzzle. Around Earth, we are used to magnetic north being imperfect but broadly connected to the planet's spin. At Uranus, the relationship is stranger. The field does not sit neatly inside the planet's sideways posture. That matters because magnetic fields are not only invisible lines in a textbook, they shape charged particles, they connect to atmospheric escape, they interact with rings and moons, they can hint at how material moves deep inside a planet. If the field is tilted and offset, then a single spacecraft path samples one slice of a system that may look different every rotation. So Voyager's discoveries all point in the same direction, but not by repeating the same lesson. The atmosphere says appearance can deceive, the rings say faint structures can be dynamically alive, the moons say small icy bodies can carry complex histories. The magnetic field says the interior and space environment are not arranged in a simple way. So that is why Uranus did not become less interesting after 1986. It became more interesting. The flyby replaced a distant blank with a set of specific problems, and specific problems are exactly what orbiters are built to solve. If Voyager had found a dead blue marble, the absence of a return might feel easier to understand. Instead, it found a system full of unfinished questions. Here is the ache at the center of the topic. The first close look was strong enough to tell us Uranus mattered, and too brief to tell us what Uranus really is. Now notice how each discovery created a fork instead of a finish line. A new moon is not only a dot added to a catalogue, it asks how the satellite formed, how it interacts with rings, what its surface records, and whether its gravity helps sculpt nearby material. A dark ring is not only a line around a planet, it asks what the particles are made of, how they survive, and what unseen bodies keep them confined. Voyager gave scientists the first close set of clues. It did not give them the long experiment. We can see this most clearly with the moons. One pass can show craters, grooves, cliffs, strange provinces. Geology is a story about sequence, which terrain came first, which fractures cut across older scars, which features are global, and which only look important because that was the hemisphere in view. Those questions need coverage, angles, and context, and the atmosphere plays the same trick. A smooth blue disk can lower expectations before the data has a chance to speak. We need to be careful with that first impression. The visible clouds at one season and wavelength are not the whole atmosphere. Winds, heat balance, methane, aerosols, vertical structure, and seasonal circulation can all hide behind a face that looks calm from far away. Here is the deeper point. Voyager transformed Uranus from a distant planet into a list of testable mysteries. That list is still active. Old magnetometer files are reanalyzed. Moon models are updated. Telescope observations keep adding seasonal context. The science has not been asleep. It has been working with a tiny local foundation. But a foundation is not a house. We can build hypotheses on it. We can compare Uranus with Neptune, with Saturn's moons, with exoplanet statistics, and with models of icy interiors. Still, the next decisive step has to come from measurements taken in the Uranian system itself. Now, the magnetic field is where Uranus stops being merely undervisited and becomes genuinely difficult to interpret. A planet's magnetic field is not a decoration. It becomes a clue to the interior, a shield and channel for charged particles, and a way the planet interacts with the solar wind. Rings, moons. Voyager found that Uranus's magnetic axis was tilted dramatically from the rotation axis and shifted away from the center. That means the field is not arranged like a tidy bar magnet through the middle of a spinning globe. It's lopsided, it becomes angled, it rotates with a planet already tipped onto its side. But one spacecraft path cannot describe that whole dance. It can cross the field at one time and place. It can measure what the particles and fields are doing along its track. It cannot sample every local time, every solar wind condition, and every rotation state. A magnetosphere like this needs repetition. Think about listening to 1 second of a complicated song. You can identify an instrument, you may catch a rhythm, but you cannot know the structure of the piece. Voyager's magnetic measurements are much better than 1 second of music, of course. Still, for a giant planet's shifting magnetic environment, the analogy helps, and the old data keeps proving the point. In 2020, researchers re-examined Voyager 2 magnetometer measurements and identified a plasmoid, a magnetic bubble that may have been carrying atmospheric material away from Uranus. The feature occupied about 60 seconds in a much larger flyby dataset. That's both thrilling and humbling. 60 seconds of old data can change how scientists think about atmospheric escape at an ice giant. But the same fact shows the weakness of the record. If 1 minute matters that much, imagine what a year of local sampling could reveal. Later reanalysis added another twist. Researchers have argued that Voyager may have encountered Uranus during an unusual solar wind compression event. In plain language, the surrounding space weather may have squeezed the magnetosphere into an uncommon state just as the spacecraft arrived. If that interpretation holds, then our only close look may have caught Uranus during a special condition. Not false, not useless, and not representative enough to settle the normal behavior. That's exactly the kind of problem an orbiter is built to solve. Now connect this to the moons. Charged particles and magnetic fields can tell us whether moons are contributing material to the plasma environment. They can help test interactions between the planet, the rings, and the satellites. If the spacecraft sees only one compressed moment, it becomes harder to separate normal sources from temporary conditions, and the tilt of Uranus makes seasonal context unavoidable. The solar wind does not meet the magnetosphere around an ordinary spinning planet. It meets a magnetic system attached to a world rolling around the sun. The geometry changes with rotation and season. That's not a small technical detail. It becomes the object of study. So what would a return mission do? It would map the field from many positions. It would watch how the magnetosphere breathes with solar wind pressure. It would measure charged particles across time. It would test whether plasma signatures come from atmosphere, moons, rings, or changing space weather. A flyby can ask these questions by accident. An orbiter asks them on purpose. Here is the difference. The spacecraft is no longer a single needle passing through a storm. It becomes a weather station moving through the storm again and again, but the field also points downward. Planetary magnetic fields are generated inside planets, in conducting layers moving deep below the clouds. So Uranus's strange magnetic geometry tells us something important about its interior. Or rather, it tells us that the interior may be unlike the simple pictures we would prefer. And this is where the planet becomes more than a destination. Uranus and Neptune are our local ice giants. Planets in this size range are common in exoplanet surveys. If we do not understand how ice giant interiors make magnetic fields, we are missing a local laboratory for a much larger planetary class. So the magnetic story leaves us with a deeper problem. The field will not sit still, and the planet beneath the field is not well constrained. To understand why Uranus remains almost unexplored, we have to go below the visible atmosphere into the cold interior that Voyager could only hint at. Now move from pictures to invisible structure. The magnetic field is one of the best reasons a single flyby can mislead us. Because a magnetosphere is not a fixed statue around a planet. It becomes a moving environment, pushed by the solar wind, twisted by rotation, shaped by whatever material comes from the atmosphere, rings, and moons. At Uranus, the geometry is almost unfair. The planet rotates on its side, the magnetic field is strongly tilted. The magnetic center is offset, so as Uranus turns, The surrounding magnetic environment does not simply spin like a neat cage. It wobbles, sweeps, opens, compresses, rearranges. A spacecraft crossing once may see a real condition that is still not the normal condition. So that is why later reanalysis of Voyager data matters so much. Scientists found a plasmoid, a magnetic bubble, in about 60 seconds of old magnetometer data. 60 seconds. In an archive from 1986, 1 minute became a new clue about atmospheric escape and the way Uranus loses material to space. But the power of that clue is also the warning. If 1 minute can change the interpretation decades later, imagine what a season of local measurements could do. Imagine watching the magnetosphere through many rotations during different solar wind conditions, while also measuring how the moons and rings supply or absorb charged particles. More recent work has also suggested that Voyager may have arrived during an unusual solar wind compression. If that interpretation is right, then some of the famous puzzles in the plasma and radiation measurements may not describe Uranus on an ordinary day. They may describe Uranus under pressure. Now think about how hard that is for science. You have one close pass. The pass is real. The instruments worked. The data are precious. The environment may have been temporarily squeezed. Without another local record, scientists have to separate planet behavior from space weather circumstance, using a single path through a changing system. An orbiter changes the question. It can measure upstream and downstream conditions. It can sample different distances and local times. It can watch the field as the planet rotates. It can compare quiet solar wind with disturbed solar wind. It can see whether plasma near a moon is persistent or occasional. And this is not only magnetism for magnetism's sake. A magnetic field connects to the interior. It can tell us something about the dynamo region, the electrically conducting layers, and the deep motion inside an ice giant. It also connects to atmospheric escape, which changes how planets evolve over long spans of time, so the field becomes a bridge between the invisible and the physical. We cannot see it in a Voyager photograph, but it may hold clues to the planet's inside, its atmosphere, and its moons. That's exactly the kind of connected problem that punishes a short flyby. The archive will keep yielding insights. That's good science. But every new insight carries the same quiet reminder. We are asking one old crossing to behave like a whole mission. Uranus deserves better than a single line through a stormy magnetic room. Now think about what it means to meet a magnetosphere only once. Around Earth, spacecraft have spent decades sampling the magnetic environment from many distances and local times. Around Jupiter and Saturn, orbiters watched fields, plasma, moons, solar wind interact again and again. Uranus gave us one fast crossing through a machine that was probably changing as Voyager passed through it. And this machine is unusually hard to summarize. The magnetic axis is tilted far from the rotation axis. The dipole is offset from the planet's center. The planet itself is tipped almost sideways. The magnetic environment does not simply sit there like a neat bubble. As Uranus rotates, the field geometry should swing through space in a way that changes what nearby moons, rings, and charged particles experience. We can make the image simple. Picture a lighthouse whose lamp is not mounted in the middle, on a tower that is itself lying on its side. The beam still exists, it still sweeps, but one boat passing once through the light cannot draw the whole coastline from that flash. So that is why the later reanalysis matters so much. When scientists found evidence for a plasmoid in about 60 seconds of Voyager magnetometer data, the discovery did not make the old encounter less impressive. It made the scarcity more visible. 1 minute buried inside a decades-old dataset could alter how we think about atmospheric escape. What else would a year of local measurements show, and what would a full tour show during different solar wind conditions? And when later work suggested Voyager may have arrived during an unusual compression of the magnetosphere, the lesson became even sharper. If the only close encounter happened during a special external condition, then our baseline may be partly event-shaped. We do not throw the data away. We treat it with more respect because we understand how narrow and precious it is. Now, Uranus carries one of the quietest mysteries in the outer solar system. It isn't only tilted, it isn't only far away, it also emits unusually little internal heat compared with Neptune and the other giant planets. For a large world built in the early solar system, that is a strange thing to find. A giant planet should hold heat from formation, compression, and internal evolution. Neptune radiates a strong internal heat flow. Jupiter and Saturn do too. Uranus, by comparison, seems muted. It becomes as if a giant world that should still be glowing from within has closed a thermal door. But we need to be precise. Scientists do not have one finished explanation. Proposed ideas include a giant impact that changed the interior, stable layering that blocks convection, compositional gradients, formation history, or other deep structural differences. The current data do not force only one answer. Here is where local exploration matters. Interior models are not built from imagination. They are constrained by mass, radius, gravity, rotation, atmospheric composition, heat flow, and magnetic field behavior. If several different interiors can fit the limited evidence, then the missing evidence becomes the story. Think of trying to infer a house from its roofline and the temperature leaking through one wall. You can make plausible plans. You can reject some impossible designs. You cannot walk through the rooms. Uranus's interior science has some of that feeling. Strong clues, weak access, multiple possible layouts. An orbiter would help by improving the gravity field. As a spacecraft moves around a planet, tiny changes in its motion reveal how mass is distributed inside. Repeated radio science passes can refine that map. A flyby can contribute, but it cannot match a sustained orbital campaign. And the magnetic field matters here too. A tilted, offset field may reflect where electrically conducting material moves inside the planet. The field is not a direct photograph of the interior, but it is a signal from the deep engine. Better magnetic mapping would narrow the range of dynamo models. Now add an atmospheric probe. The atmosphere is the accessible skin of the planet, but it carries chemical memory. Noble gases, isotopes, and deep composition can tell us about formation and migration. These measurements cannot be cleanly guessed from far away. A probe has to enter, sample, and transmit. So that is why a dedicated mission includes both orbiter and probe in the decadal concept. The orbiter watches the planet and system over time. The probe provides direct composition from the atmosphere. Together they connect the outside of Uranus to its hidden origin story. But even this is not simple. Dropping a probe into Uranus is not like lowering a thermometer into water. It needs a heat shield, a power source, instruments, a stable descent, a relay geometry to the orbiter. It has to survive entry, measure quickly, and send data before the environment ends the mission. The interior mystery also explains why Uranus matters beyond itself. Many exoplanets fall into the broad size range between Earth and Neptune. We do not have local samples of those distant worlds. We have Uranus and Neptune. If one of our two ice giants is poorly understood, our comparisons elsewhere are weaker. Now, this does not mean Uranus is a perfect stand-in for every exoplanet. It isn't. Exoplanet categories are often based on mass and radius, not direct composition. But local ground truth still matters. The physics of interiors, atmospheres, and magnetic fields has to be tested somewhere. And Uranus is the colder, quieter, stranger member of the pair. Neptune has been visited once too, but Uranus became the decadal priority for a dedicated large mission. Part of the reason is scientific value, and part is architectural feasibility. The mission case is not casual. It's built on the need to understand ice giants as a class, so the cold interior turns the title question into something larger. We are not merely missing better images. We are missing the deep structure of one of the solar system's major planet types. That becomes a different level of unknown. And because the interior touches the atmosphere through heat, circulation, composition, weather, the next step is to look upward again. Uranus does not only hide inside itself, it also changes slowly under seasons so long that a human career can cover only part of one Uranian year. Now let the camera sink below the blue-green cloud tops. The visible face of Uranus is not the deepest mystery. The deeper puzzle is the engine, or perhaps the missing engine, inside the planet. Giant planets are expected to carry heat from their formation. Jupiter radiates more energy than it receives from the Sun. Saturn does too. Neptune, the other ice giant, has its own strong internal heat. Uranus is the strange sibling. It releases very little internal heat compared with what planetary scientists expected. That fact can sound small until we translate it. A giant planet is not a rock sitting cold in space. It becomes a layered, compressed, chemically rich world whose interior should still remember how it formed. Heat is a messenger from that hidden interior. If the messenger is faint, something about the inside is unusual. Scientists have proposed several possibilities. Maybe Uranus suffered a giant impact early in its history, one connected to its extreme tilt, and that event changed how heat moves. Maybe the interior is layered in a way that prevents convection, so warmth remains trapped below instead of rising easily. Maybe composition gradients separate materials by density. Maybe our models are missing a more subtle part of ice giant physics. We should not pretend one answer has won. The point is the opposite. Multiple interior stories can fit the limited evidence because the direct constraints are sparse. Mass, radius, heat flow, atmospheric composition, magnetic field, and gravity all help. The close spacecraft record is still thin. An orbiter would not drill into Uranus. It would do something more delicate. It would trace the gravity field by tracking tiny changes in the spacecraft's motion. It would map the magnetic field repeatedly. It would connect atmospheric measurements to interior models. It would test whether the planet is arranged in broad layers, mixed regions, or something stranger. The atmospheric probe is crucial here. Certain gases and isotopes act like fingerprints from formation. Noble gases, deep abundances, and isotope ratios can tell us about the material that built Uranus and the conditions in the early solar system. Remote telescopes cannot cleanly measure all of that from far away. A probe must fall into the atmosphere and sample the air directly. That descent would be brief compared with an orbital tour, but it would be a different kind of truth. For a little while, the mission would stop inferring the atmosphere from light and start measuring it from inside. Temperature, pressure, composition, clouds, winds would become a vertical profile instead of a distant estimate, and that profile would reach beyond Uranus. Ice giants are central to exoplanet interpretation because many known worlds fall into Uranus and Neptune-like size ranges. We cannot visit those exoplanets. We barely know what their interiors are. Our local ice giants are the test cases, and one of them has had only one flyby. So a cold interior is not a side mystery. It's one of the reasons Uranus matters as a planet. If we do not understand why Uranus is so internally quiet, we are missing a key variant in how giant planets cool, layer, mix, evolve. This becomes where the science becomes almost intimate. The planet looks calm because we are far away. It may be calm because its interior is genuinely strange. Or it may only look calm because our measurements are too thin to hear the machinery. A dedicated mission would finally let us listen for the machinery properly. Now move from the magnetic field into the planet's body. Uranus is often introduced by its tilt, but the heat problem may be just as revealing. Giant planets are not supposed to be cold in a simple way. They carry leftover energy from formation, from compression, from slow internal rearrangement. Neptune, Uranus's sibling in size and distance, leaks much more internal heat. So Uranus asks an uncomfortable question. Did something happen early in its history that changed the way heat escapes? Did a giant impact tip the planet and leave the interior stratified? Are layers inside the planet preventing convection like a sealed pot that cannot stir? Or are our measurements still too sparse to choose between several possible interiors? We do not need to force one answer. The uncertainty is the story. From the outside, Uranus gives us mass, radius, atmospheric clues, magnetic clues, a limited gravity picture. Models can fit those constraints in more than one way. Inside those models are different amounts of rock, ice, gas, heat, layering, motion. Without better measurements, the hidden planet remains partly negotiable, and here the atmospheric probe becomes more than a dramatic descent. It becomes a key to formation history. Noble gases and isotopes are like fingerprints from the early solar system. They can tell us where material condensed, what ingredients were trapped, and how this ice giant differs from Jupiter. Saturn, Neptune, and Orbiter can map gravity and magnetism. A probe can sample the gases directly. Together, they would tighten the interior story from two sides. We should feel the scale of what is missing. The question is not whether Uranus has clouds or rings or moons. The question is what kind of giant planet it is under the clouds. Until we know that, we are using one of our only local ice giants as a partially opened book. Before the seasonal clock enters the story, let's restate where the middle of the case has taken us. The evidence now shows that Uranus is not merely far away and pale. Its magnetic field points to an unusual interior, while its weak internal heat makes the planet harder to explain with simple giant planet intuition. So the next question is how a world with that strange interior behaves when the sun illuminates it on a schedule almost no spacecraft mission has ever been able to watch from inside the system. Now time becomes part of the instrument. Uranus takes about 84 Earth years to orbit the Sun. Because it is tilted almost onto its side, its seasons are extreme. One pole can face long sunlight while the other sits in darkness. A single spacecraft flyby near one solstice cannot represent that whole cycle. Voyager saw Uranus near southern summer. That fact shapes the archive. It affected the visible atmosphere, the lighting on moons, and the context of the system. The spacecraft did not arrive at equinox. It did not watch the planet move from one season to another. It caught one powerful seasonal moment. But seasons on Uranus are not decorative. They drive sunlight, temperature contrasts, atmospheric circulation, cloud patterns, haze, possibly auroral behavior. On Earth, we would never claim to understand weather from one afternoon. On Uranus, the afternoon lasted only hours and the year lasts a lifetime. So remote observing becomes essential. Hubble, large ground telescopes, and Webb-era observations have extended the timeline. They let scientists see Uranus under different solar angles, different cloud states, and different upper atmosphere conditions. Without those observations, the Voyager record would be even more isolated. And we should be fair to telescopes. They are not second-rate simply because they are far away. They can monitor change over decades. They can revisit Uranus when no spacecraft is there. They can reveal seasonal evolution that Voyager could never wait to see. But telescopes have limits that matter to the central question. They cannot directly measure deep atmospheric composition. They cannot sample noble gases and isotope ratios. They cannot follow a parcel of atmosphere down through pressure levels. They cannot map local winds and fields from within the system. A probe would do something remote sensing cannot. It would descend. It would measure temperature, pressure, composition, cloud structure, chemical ratios along a vertical path. Even one probe would not answer everything, but it would anchor the atmospheric models in a way no telescope can. Now imagine combining that with an orbiter. The orbiter watches clouds, tracks storms, measures the gravity and magnetic field, relays probe data. It returns to the planet again and again as conditions change. The atmosphere stops being a pale disk and becomes a moving system. The seasonal issue also changes how we interpret Voyager's bland images. Uranus looked quiet in visible light during the flyby. Later observations showed more atmospheric activity as viewing geometry and seasons changed. That does not mean Voyager was wrong. It means Voyager saw one state. And one state is not a climate. A climate is a pattern across time. It includes what repeats, what shifts, and what only appears under particular solar conditions. Uranus's long year stretches that pattern beyond the patience of a flyby mission. This becomes one reason the phrase almost unexplored remains scientifically honest. We do have observations over time from Earth and space telescopes. We do not have local seasonal exploration. The gap is not total darkness. It becomes the gap between watching a distant performance and placing instruments on the stage. Now bring the rings and moons back into view, their illumination changes too. A moon surface that was shadowed or poorly lit in 1986 could tell a different story under another season. Ring opening angle and viewing geometry change what structures can be detected. Time alters the question, and because Uranus moves so slowly, missed opportunities echo. If you want to observe a particular seasonal geometry from close range, the calendar is not flexible in the ordinary way. A mission launched in one decade arrives in another, and the planet's orientation at arrival may matter for science planning. So the seasonal record teaches a larger lesson at Uranus. Exploration is not just about reaching a place. It becomes about reaching a place at a useful time, staying long enough for change to matter, and carrying instruments that can separate surface appearance from deep physical behavior. Now we can follow that lesson outward. The same limited light and time that narrowed our view of the atmosphere also narrowed our view of the moons. And the moons may be where the idea of Uranus as a quiet, finished system breaks most dramatically. Now bring time back into the story. Uranus takes 84 Earth years to orbit the Sun. That means a season on Uranus lasts longer than many spacecraft missions, longer than many research careers, and long enough to turn patience into a scientific requirement. Because the planet is tilted so dramatically, those seasons are not gentle. One pole can face the Sun for decades, while the other sits through a long night. The equator, the mid-latitudes, the poles, and the upper atmosphere all move through a seasonal rhythm unlike the one our intuition expects. Voyager saw one part of that rhythm near southern summer solstice that becomes a valuable timestamp. It isn't the full calendar. If someone studied Earth only from a short aircraft pass over Antarctica in midsummer, we would not call that a finished climate record. We would call it an extraordinary glimpse taken at a very particular moment. Remote observations have made that record much richer. Hubble, ground-based telescopes, and infrared observatories have watched Uranus change after Voyager. Bright cloud features appeared. Seasonal bands shifted. Modern instruments have looked at upper atmospheric emissions and auroral behavior. These observations prove that Uranus is not the static blue disk it once seemed to be. But again, the help has a boundary. Telescopes give us time. They do not give us touch. They can follow clouds and temperatures in broad ways, but they cannot measure the deep atmosphere directly. They cannot feel winds at different pressures. They cannot sample noble gases. They cannot carry a package of instruments under the haze and through the layers. An orbiter and probe together would connect the timeline to the vertical structure. The orbiter could watch the atmosphere over years, tracking storms, waves, temperatures, and seasonal change. The probe could provide one deep column of direct measurements. Together they would link what changes from above with what the air is actually made of below. This matters because seasons can fool us. A planet may look bland at one season and active at another. A circulation pattern may strengthen or fade. Clouds can appear at latitudes that once seemed quiet. If the planet's response to sunlight is unusual, that response may also tell us about heat flow from within. So the seasonal question ties back to the cold interior. Uranus receives weak sunlight, releases little internal heat, and rotates on its side. Those facts are not separate trivia. They are interacting pieces of one climate puzzle. How does an atmosphere move when the energy sources are so strange? A flyby cannot answer that, because a season is not a moment, it becomes a process. Voyager gave us a date on the calendar. Telescopes have filled in some later pages. A resident spacecraft would finally write in the margins every day, comparing what the planet does with what the Sun, the interior, and the magnetic environment are doing at the same time. And we need that kind of record because Uranus is a slow planet. It does not perform for us on human schedules. If we want to know it, the mission has to adapt to Uranus's clock, not ours. Now let the season run in your mind. On Earth, a classroom can watch the sun's path change over a school year. On Uranus, the same seasonal story stretches across generations. A child born when one pole is leaning toward the sun could be middle-aged before the equator takes its turn, and elderly before the opposite pole receives the same long attention. That slow clock matters because atmospheres remember sunlight, methane clouds, hazes, upper atmosphere temperatures, winds, and storms can all respond to changing illumination. The response may lag, it may differ by altitude, it may depend on chemistry we have not measured directly. A single flyby near southern solstice cannot tell us how the whole machine breathes over an 84-year orbit. Remote observing gives us the patience Voyager did not have. Hubble large ground telescopes and newer infrared observations can follow Uranus as the viewing geometry changes. We can see bright features appear. We can track broad atmospheric behavior. We can watch the planet stop looking quite so blank. That long baseline work is one reason Uranus is not scientifically abandoned. But we still run into the same boundary. From far away, we mostly read the top of the system, we infer. We compare wavelengths, we model. We cannot drop instruments through pressure levels and measure composition directly. We cannot measure noble gases from a telescope. We cannot follow a parcel of atmosphere from cloud top to depth. So an orbiter and probe would not replace remote telescopes. They would anchor them. The probe would give a vertical truth line through the atmosphere. The orbiter would connect that local descent to global weather and seasonal context. Then Earth-based and space telescopes could extend the timeline with much firmer ground under their interpretations. Now the Uranian system is not just one planet. It's rings, small moons, and 5 large classical moons with histories we have barely sampled up close. Voyager gave us the first close portraits of Miranda, Ariel, Umbriel, Titania, Oberon. Those portraits were valuable. They were also incomplete. The lighting problem returns immediately. Voyager's path and Uranus's season limited what hemispheres could be seen. Some terrain was well placed, other terrain was not. For geologic worlds, light and angle are not minor details. They decide whether cliffs, craters, fractures, and young surfaces can be interpreted. Miranda is the famous case because it looked almost impossible at first glance. Its surface showed huge canyons, patchwork regions, and signs of violent geologic rearrangement. A small moon should not look that complicated without a story. Voyager showed the story existed, but not the whole plot. Ariel, Umbriel, Titania, and Oberon matter too. They are not as culturally famous as Europa or Enceladus, but they are large enough to preserve records of heating, impacts, tectonics, possible internal evolution. Their surfaces are pages from the Uranian system's history, and many of those pages are still poorly lit or poorly resolved. Now add the recent modeling, NASA/TPL reported work suggesting that Ariel, Umbriel, Titania, and Oberon may contain ocean layers between icy crusts and deeper interiors. While Miranda may now be frozen, this becomes important, but the wording matters. These become model-based inferences, not confirmed ocean worlds. That distinction protects the science. A model can be strong and still not be a direct detection. It uses Voyager observations, later data, chemistry, thermal evolution, comparison with other icy moons. It narrows possibilities. It does not replace a spacecraft flying the needed tests. So what would confirmation require? We would want repeat flybys or orbital geometries, better topography, improved geology, gravity measurements, and magnetic induction constraints where possible. We would want to know whether any ocean is present today, how salty it might be, how thick the ice shell is, and whether the surface has exchanged material with the interior. But even magnetic induction may be harder at Uranus than at some other ocean worlds. Cold, chemically different oceans may conduct electricity less effectively. That means a future mission may need careful geometry and multiple kinds of evidence. Again, the answer is not one magic instrument. It becomes a campaign. The rings add another layer. Uranus's rings are dark and narrow, tied to small moons and dust processes that are not fully understood. Rings are dynamic systems. They change through collisions, shepherding, impacts, gravitational nudges. A flyby can reveal structure, an orbiter can watch behavior. And the small moons matter because they can maintain, disturb, or feed ring material. The Uranian system is a collection of interactions, not a planet with decorative accessories. If we want to understand the system, the orbiter has to divide time among atmosphere, field, rings, moons. Now we can see why a Uranus mission becomes a flagship-scale problem. The science menu is too broad for a simple camera pass. The spacecraft must be able to study the planet and its environment, while also making meaningful close observations of moons and rings. Every target competes for time, data, and trajectory. This becomes where the ocean question can easily become hype, so we should keep our footing. The Uranian moons are not confirmed habitats. They are possible ocean-bearing worlds based on models and limited evidence. That's enough to make them scientifically important without turning them into a lifebait promise. And for the viewer, the emotional shift is subtle. Uranus stops being a lonely blue disk. It becomes a half-seen system of worlds in the dark, with fractured moons, narrow rings, and model-based possibilities waiting for local tests. One flyby cannot do justice to that kind of place. So if the science case is so strong, the obvious question returns. Why not just send the spacecraft? Why not choose a launch date, build an orbiter, add a probe, and go? The answer is that the word just disappears as soon as we translate it into physics. Now leave the planet for a moment and move outward to its moons. This becomes where Uranus stops being a single object and becomes a system. Rings, small moons, and 5 large classical moons surround the planet, and Voyager saw only a narrow version of that family. Miranda became the image people remember because it looked almost broken and reassembled. Its cliffs, grooves, and patchwork regions suggested a violent or complicated past. The other large moons also matter. Ariel, Umbriel, Titania, and Oberon are not background ornaments. They are icy worlds with surfaces that may record internal heating, impacts, resurfacing, and long quiet histories. Voyager's lighting and path limited what could be mapped. Some terrains were well placed, others were poorly lit or simply not seen with the detail scientists would want. For geology, that matters enormously. A crater count can suggest surface age, a fault can suggest internal stress, a smooth region can hint at resurfacing. But those interpretations grow stronger when the map is global and the lighting is varied. The ocean question raises the stakes. NASA and JPL have discussed modeling work, suggesting that Ariel, Umbriel, Titania, and Oberon may contain ocean layers. While Miranda may be frozen now, that's fascinating, but we have to say it carefully. These become model-based inferences, not direct confirmations of living ocean worlds. The difference is important. A model can combine Voyager images, moon sizes, densities, thermal histories, chemistry, and comparisons with other icy worlds. It can show that an ocean layer is plausible or even likely under certain assumptions. But direct evidence requires more. It requires measurements that respond to the moon itself. A mission could look for clues in several ways. Gravity measurements could reveal mass distribution. Better imaging and topography could show whether the crust moved recently. Thermal mapping could search for unusual warmth. Magnetic induction measurements might test for electrically conductive layers, though cold, salty oceans can be difficult to detect. Repeat flybys could compare one moon with another instead of treating the system as a set of old portraits. And the rings are part of the moon story. Small moons can shepherd ring material, dust can move, impacts can feed faint structures. A dark ring system at the edge of sunlight may be changing in ways we have never watched close up. Voyager saw enough to tell us the system was real. It did not give us a long movie of how it works. The moon system matters because it fights the simplest version of the Uranus story. The planet is not merely a blue ball that needs a better weather report. it becomes the center of an underexplored satellite system. Some of the most interesting answers may be orbiting beside it, in icy bodies whose surfaces hold clues to heat and water in the outer solar system. Now compare that with the record we have. A few close hours, one season, limited lighting, no return flybys, no orbiter tour, and no dedicated moon campaign. The mismatch is almost painful. The science questions have become more ambitious, while the local data remain anchored to 1986. So when someone asks why we do not just send a camera back, the moon system gives the first correction. The mission does not only need a camera, it needs time, navigation, repeat geometry, field instruments, gravity science, thermal planning, and enough orbital design to visit different targets without wasting the mission on a single beautiful pass. Now look at the moons as a system, not as a set of names. Miranda, Ariel, Umbriel, Titania, and Oberon orbit in the cold outskirts of a tilted planet. They have lived through impacts, tides, internal freezing, possible heating episodes, and long darkness. Voyager gave us close glimpses of them, but it did not give each moon a complete biography. The possible ocean question makes that incompleteness matter. NASA/TPL reporting on modeling work suggests that several large Uranian moons may contain ocean layers, while Miranda may be frozen now. We have to say that carefully. These become inferred oceans in models, not confirmed seas detected by a spacecraft flying magnetic induction experiments around each moon. But even as inference, the possibility changes the emotional weight of the system. A moon that looks like a cold ball in a distant image may hold a layered interior, salts, ammonia, an old ocean, or a frozen record of one, if that is even plausible for Ariel, Umbriel, Titania, or Oberon. Then the Uranian system is not a museum of dead ice. It becomes a set of unresolved worlds, and resolving them would require the kind of patience a flyby cannot offer. We would want repeated passes, different lighting, better topography, gravity clues, surface composition, magnetic measurements sensitive enough to test for conductive layers. We would want to compare moons against each other, because the differences may reveal the history of heating and cooling across the system. Or here is why this belongs in the central question. The moons are not a side quest. They are one reason Uranus remains almost unexplored. A planet with a family of barely mapped icy worlds is not fully known just because one spacecraft photographed parts of them once. Now we turn from what is missing to what a return would demand. Uranus orbits around 19 times farther from the Sun than Earth. That number sounds neat on a page, but for a spacecraft it changes everything. Sunlight, temperature, communication, flight time, power, propulsion, risk. At Uranus, sunlight is hundreds of times weaker than it is here. Solar panels that work beautifully near Earth or Mars become a difficult proposition. A serious outer planet mission usually needs radioisotope power, the kind that uses heat from radioactive decay to make electricity and keep systems alive. And power is not just a battery problem. Power decides which instruments can run, how much data can be processed, how warm the spacecraft can stay, how often it can communicate, how much margin engineers have when something behaves unexpectedly. Far from the Sun, every watt has a job. Now think about the cold. A spacecraft cruising for more than a decade must keep electronics, fuel lines, mechanisms, instruments within survival limits. It cannot depend on sunlight for comfort. Thermal design becomes part of the mission's nervous system. Heat is budgeted almost like fuel. Communication changes too. Voyager's signals took hours to reach Earth during the Uranus encounter. A modern orbiter would still work across multi-hour light time. Commands cannot be interactive in the human sense. Data come home slowly through a high-gain antenna and the deep space network, with careful scheduling. So a return mission has to think like a remote outpost. It stores data, it waits for downlink windows, it compresses and prioritizes observations, it keeps itself safe through long delays. The mission team cannot simply steer it moment by moment like a drone. Now add cruise time. Concept studies for Uranus orbiter and probe have examined early 2030s Jupiter gravity assist opportunities with cruise times around the low to mid-teens of years, and later alternatives with different routes. These become concept study examples, not final mission facts. They show the scale. A spacecraft launched in one era may arrive in the next. Scientists, engineers, budgets, institutions, and public attention have to endure across that arc. A mission to Uranus is not a project that pays off quickly. It becomes a generational commitment. And then comes mass. Every instrument, tank, heater, antenna, computer, shield, structure adds weight. More mass can require more launch energy. More launch energy can require a different rocket or a gravity assist. A change in one subsystem moves through the whole design. So that is why another flyby would not solve the central problem. We could imagine sending a fast spacecraft past Uranus again. It might improve images, update measurements, and add a second point in the record. But the science case now asks for an orbiter and atmospheric probe. It asks for residence. Residence means arriving with enough capability to work for years. It means power that lasts. It means communication plans that can return useful data. It means an orbit tour that balances atmosphere, fields, rings, moons. It means an atmospheric probe released at the right time and geometry. So the phrase "go back" hides a staircase. First, leave Earth with enough energy, then survive the cruise. Then reach the planet at the right speed and angle, then slow down or otherwise become captured, then deploy a probe. Then operate through years of distant, low-power science. Now none of this means Uranus is impossible. That would be the wrong conclusion. The Decadal Survey did not recommend a fantasy. It recommended a serious flagship-class mission concept because the science return is large and the architecture is plausible. Hard does not mean unreachable, but hard does mean rare. Only a few missions in a generation can occupy this class. A planetary program has to choose between many strong science cases. Outer-planet flagships do not only spend money, they occupy workforce, launch opportunities, radioisotope power supply, DSN time, and institutional attention. So when someone asks why we have not simply gone back, the honest answer begins with the word simply. There's no simple version of the mission that answers the question properly. The next problem is timing, because the route to Uranus is not always equally favorable. Now the documentary turns from what we are missing to what it costs to stop missing it. At first, going back sounds like a matter of will. We went once, rockets are better now, cameras are better now, and computers are better now, so why not launch another spacecraft and correct the gap? The answer begins with distance. Uranus orbits about 19 times farther from the Sun than Earth does. Sunlight there is only a tiny fraction of what spacecraft enjoy in the inner solar system. Solar panels that work near Mars, or even Jupiter, become far less attractive when the Sun shrinks to a cold, bright star. That pushes the mission toward radioisotope power. An outer-planet spacecraft needs electricity for instruments, computers, heaters, communication, and propulsion support. It also needs warmth, because deep space is not gentle to hardware. Power is not an accessory at Uranus. It's survival. Every watt becomes part of the science plan. A camera competes with a spectrometer. A transmitter competes with a heater. A long observation competes with data storage and downlink. A spacecraft at Uranus cannot behave like a limitless observatory. It becomes a carefully rationed machine operating across billions of kilometers. Communications are another quiet constraint. During Voyager's Uranus work, signals took hours to reach Earth. A modern mission would still deal with multi-hour one-way light time. Controllers cannot joystick the spacecraft. The mission has to plan, store, compress, prioritize, and send data through a narrow link to Earth. The Deep Space Network becomes part of the mission's body. Giant antennas on Earth must listen at the right times. Other missions need those antennas too. Data from Uranus travels slowly, and the most valuable observations may have to wait their turn through a schedule built across the whole solar system. Then there is cruise time. A spacecraft to Uranus does not arrive in a few months. Concept studies often discuss journeys around the low to mid-teens of years, depending on route and assists. That means a mission team must design hardware that survives launch, years of quiet travel, a critical arrival, and then several more years of science. A long cruise also changes human planning. People graduate, retire, change jobs, hand responsibilities across generations before the first close data arrive. Budgets must hold, institutions must keep knowledge alive. The spacecraft must remain healthy while the public sees almost nothing happen except distance accumulating. But the hardest correction is this: another flyby would not answer the central science. It would improve the record, but it would not transform it in the way the decadal survey recommendation imagines. The true step is an orbiter with an atmospheric probe. That mission must arrive, slow down, work locally, distribute its resources across a whole system. So going back is not one action. It becomes a chain of launch, cruise, power, heat, navigation, communication, arrival, capture, probe release, orbit tour, data return, and years of operations. Break one link and the scientific promise changes. So that is why Uranus remains almost unexplored in a way that feels different from neglect. The obstacle is not a locked door with a simple key. It becomes a staircase where each step is heavy, expensive, and connected to the next. Now translate the simple phrase "go back" into a spacecraft on a workbench. It needs power before it needs poetry. It needs heat. It needs a radio system. It needs propulsion, instruments, shielding, software, memory, fault protection, a plan for surviving years when no repair crew can reach it. Every kilogram has to justify itself before launch. At about 19 times Earth's distance from the Sun, solar power becomes a much harder bargain. A spacecraft can carry enormous solar arrays in some deep space missions, but Uranus pushes the trade toward radioisotope power and careful thermal design. Watts are not abstract. Watts decide which instruments can run, which heaters stay on, how much data can be gathered, and how much margin remains when something ages. And cold is not just a background mood. Propellant lines, batteries, electronics, instruments, and mechanisms all have temperature limits. A mission can use insulation, heaters, and radioisotope heat. Those choices feed back into mass and power. The deeper we go into the outer solar system, the less free anything feels. Communication adds another constraint. A command does not arrive instantly. A signal from Uranus takes hours to cross the solar system, depending on the planet's positions. The spacecraft must operate with autonomy, store data, point a high-gain antenna accurately, wait for precious deep space network time on Earth. A beautiful observation can become less useful if it cannot be returned within the mission's data budget. So the return mission is not a bigger camera. It becomes a long-duration machine built around scarcity, scarce sunlight, scarce power, scarce downlink, scarce mass, scarce launch opportunities. Once we see that, the lack of a return stops looking like a simple absence and starts looking like the shadow cast by a very demanding mission architecture. Before launch windows take over, let's gather the practical problem we have just built. By this point, Uranus is not only a planet waiting for better pictures, it is a system of moons, rings, fields, atmosphere, and deep composition that requires residence, repeated passes, and an atmospheric probe. So the next question is why, once that need is clear, the act of getting a spacecraft there still becomes one of the hardest choices in planetary exploration. Now orbital mechanics enters the room. A spacecraft can travel to Uranus in more than one way, but the route changes what the mission can carry, how long it takes, how fast it arrives, what risks it accepts. In deep space exploration, the calendar is part of the engine. Gravity assists are the easiest piece to misunderstand. They are not free magic, and they are not decorative loops on a mission poster. A gravity assist uses the motion of a planet to reshape a spacecraft's path. It can help deliver mass, reduce launch energy, or set up an arrival speed the mission can handle. Jupiter is especially valuable for outer planet routes because it is massive and already far from the Sun. Concept studies for Uranus orbiter and probe examined early 2030s opportunities using Jupiter gravity assists. Other concepts can use inner solar system assists and longer paths. The exact numbers belong to studies, not to a final approved mission. But the lesson is stable. Missed windows do not make Uranus vanish, they change the trade. A later or different route may require more time, more thermal survival, different launch energy, less delivered mass, or different operations planning. The planet is still there. The mission changes shape. Now this is where Uranus becomes a planning problem as much as a destination. Launch windows must align with spacecraft readiness, budget, rocket availability, radioisotope power, workforce approval. The sky may offer a path, but institutions and hardware must be ready to take it. Think of a train that comes only occasionally, but the ticket is a spacecraft that took years to build. If the spacecraft is not ready, the train leaves. Another route may exist, but it may be slower, costlier, or force you to carry less. That's what timing can feel like at planetary scale. And timing reaches all the way to arrival. The spacecraft's speed at Uranus matters. A flyby can be fast because it does not need to stay. An orbiter has to deal with that speed. The route that gets you there is tied to the price of stopping once you arrive. So a mission designer is always balancing. Faster cruise can mean higher arrival energy. More delivered mass may require a gravity assist. A gravity assist requires calendar alignment. A longer cruise increases operations time and survival demands. There's no one variable called go. Now add radioisotope power. Trade reporting has highlighted plutonium and RTG availability as a constraint for future planetary missions, including timing discussions around Uranus concepts. We should treat that as reported programmatic context, not as a permanent law, but it shows how a scientific priority can wait on supply chains far from the telescope image. The launch vehicle matters too. The decadal materials described a Uranus mission as viable with available launch vehicles in the relevant decade, but viability is not the same as assignment. A real mission still needs selection, formulation, budget, hardware, schedule discipline. Here is why recommendation and launch date must not be confused. The decadal survey can say the science community's highest new large mission priority is Uranus orbiter and probe. That statement is powerful. It does not bolt a spacecraft to a rocket. Now the window problem also protects us from a false villain. If a mission misses an ideal Jupiter assist family, that does not prove nobody cared. It may mean the project was not approved, powered, funded, or built in time to use that route. The missed geometry is a symptom of a larger chain, and the chain is exactly what this video is about. Distance becomes power, power becomes mass. Mass becomes launch energy. Launch energy becomes timing, and timing becomes program choice. That program choice becomes decades of presence or absence in the archive. So the answer to why Uranus remains almost unexplored is now more concrete. The planet needs a spacecraft that can arrive with enough capability to stay, and the best ways to deliver that spacecraft are bound to rare celestial timing. But arrival is still not success. Once the spacecraft reaches Uranus, it has to stop. Now we reach the calendar, which sounds ordinary until gravity enters the room. A launch window is not just a date people choose because the budget happens to be ready. For outer planet missions, timing decides how much energy the spacecraft needs, how much mass can arrive, how long the cruise lasts, how fast the spacecraft approaches its target. Gravity assists are central to this. A spacecraft can pass near a planet and steal a little orbital help, changing speed and direction without carrying all the propellant itself. The maneuver is elegant, but it comes with a bargain. The assisting planet has to be in the right place at the right time, and the route after the assist must still serve the mission. Voyager itself existed because of a rare planetary alignment that made the outer planet tour possible. A Uranus orbiter is not the same kind of grand tour mission, but it still faces the calendar. Concept studies have examined early 2030s Jupiter gravity assist opportunities, along with later alternatives involving inner solar system assists. Those values are examples from mission studies, not a launched mission plan. That distinction matters. A concept can say, under these assumptions, this route could deliver this kind of spacecraft in this kind of time. It isn't the same as NASA saying the spacecraft is built, funded, and scheduled. Mission design is a map of possibilities before it is a ticket. If a favorable Jupiter assist is available, it may improve delivered mass or reduce energy demands. If that family of windows passes, Uranus does not become impossible. The trade-offs shift. The spacecraft may need a different route, a longer cruise, different thermal planning, different operations assumptions, or a different delivered mass. Now add the other calendars. Radioisotope power supply has its own production and allocation reality. Launch vehicles have schedules. Flagship budgets move through federal planning. Engineering teams have workforce limits. The deep space network has future demand. A good celestial window can arrive before the institutional window is ready. And that mismatch is one of the least dramatic but most important parts of planetary exploration. The planets do not wait for appropriations. Budgets do not bend automatically around Jupiter's position. A scientifically ideal opportunity can be missed because the mission has not reached approval, because power systems are not available, because another flagship is already consuming resources, or because the program has not finished earlier commitments. Here is why not now has several answers at once. There's the physics answer, route, energy, arrival speed. There's the engineering answer, mass, power, thermal design, and reliability. There's the program answer, money, workforce, launch vehicle, plutonium, and schedule. None of these alone explains everything. Together they create the real window problem. For a calm documentary, this is where the antagonist becomes clear. The antagonist is not a villain, it becomes alignment. The alignment of planets, resources, institutions, decades. Uranus sits far away, moving slowly, while our ability to reach it depends on a rare agreement between the sky and the people building machines under it. So a missed window is not simply a lost appointment, it can reshape the entire mission architecture. The question becomes less like, why has nobody bought a ticket? And more like, how do you send a complete laboratory to a distant world when the train schedule is written by gravity? Now bring Jupiter into the story, because sometimes the fastest path to Uranus is not aimed only at Uranus. A gravity assist uses a planet's motion to reshape a spacecraft's path. It can add energy, change direction, and reduce what the launch vehicle must provide. The assist is available only when the calendar and geometry cooperate. That makes launch windows feel almost biological. They open, they close, and they return in different forms. A mission concept may look especially attractive in one family of years because Jupiter is in the right place. Miss that family, and Uranus does not vanish. The route changes, the cruise may lengthen, the delivered mass may change, thermal conditions, operations complexity, and risk can all shift. We need to keep the language disciplined here. Early 2030s Jupiter assist opportunities and low to mid-teen cruise times appear in concept studies. They are examples of mission design, not promises that a spacecraft is already scheduled. Later alternatives can use inner solar system assists. But those routes come with their own timing and heat management complications, and trajectory is only one calendar. The spacecraft must also meet the calendar of budgets, launch vehicles, workforce, instrument development, radioisotope power supply, review milestones, deep space network planning. A window in the sky does not automatically create a window in a planetary program. Here is the frustrating part. Physics may offer a good route before institutions are ready to fly it. Institutions may become ready when the easiest route has passed. Then engineers have to redesign the bargain. The planet remains reachable, but the price changes. So the window problem is not an excuse. It becomes a real coupling between the solar system and human planning. Uranus sits far enough away that timing becomes a resource. Waste that resource, and the mission is still possible, but it may become heavier, longer, riskier, or harder to approve. Now we can make the window problem more human. Mission teams do not simply ask, can we get there? They ask what kind of spacecraft arrives when the route is finished. Does it arrive with enough mass to carry the instruments? Does it arrive slowly enough for capture to be manageable? Does it arrive while the science geometry is useful? and as the crews expose the spacecraft to heat near the inner planets or too many years of aging before the real work begins. And we have to keep two maps in our head at once. One map is celestial, Jupiter's position, Uranus's position, launch energy, arrival speed, and the shape of the crews. The other map is human, when engineers can build, when funding can ramp up, when radioisotope power units can be delivered, when launch vehicles are available, and when a mission can pass the reviews that protect a flagship from wishful thinking. So if we hear that a study examined a 2031 or 2032 Jupiter gravity assist, we should treat that as a design opportunity, not as a broken appointment. The opportunity shows what the solar system was offering. It does not prove the program was ready to accept it. A mission concept can be scientifically mature enough to recommend and still institutionally early enough that the best sky window is difficult to use. Here's the quiet consequence. The longer a Uranus mission waits, the more the design has to negotiate with a different solar system. We may still get there. We may still build a powerful orbiter and probe. The bargain will not be identical to the one described in earlier studies. The route, the time of flight, the power needs, the arrival conditions may all shift. So that is why launch windows belong in the answer to the title. They are not calendar trivia. They are one of the ways distance turns into delay. Now we reach the line between passing a planet and exploring it. A flyby can use the planet as a turning point in a long journey. An orbiter has to arrive and lose enough speed for Uranus to capture it. That single difference changes the mission from a visit into a commitment. Stopping in space does not mean pressing a brake pedal. It means changing velocity with propulsion, atmospheric drag in some advanced concepts, or a carefully designed sequence of maneuvers and flybys. The spacecraft must spend energy to transform a fast arrival into a bound orbit. Chemical orbit insertion is mature and understandable, but it costs mass. Propellant carried for the final burn is propellant that had to be launched from Earth, accelerated through the solar system, kept usable for years, and protected through the cruise. The stopping fuel travels the whole way with you. Arrow capture appears in mission architecture studies as an intriguing trade. In that approach, a spacecraft uses a planet's atmosphere to slow down, reducing propellant needs. But arrow capture is not the selected decadal baseline for Uranus, and it carries its own risks: heat, guidance, atmospheric uncertainty, technology readiness. So we should use arrow capture carefully. It shows how hard the stopping problem is. It does not mean a Uranus mission already has a chosen shortcut. The safe point is broader. Becoming an orbiter requires paying an energy bill that a flyby avoids. Now layer in the atmospheric probe. The probe cannot simply be tossed overboard whenever convenient. It needs an entry path, a heat shield, instruments, power, a relay geometry back to the orbiter. It must enter at the right angle and survive long enough to send the measurements that matter. Those measurements are precious because they reach questions no orbiter can fully answer from above. Noble gases, isotope ratios, deep atmospheric composition, cloud layers, temperature, pressure, winds along the descent path all help constrain formation and interior models. A probe gives the planet a chemical voice, but probe delivery competes with everything else. The orbiter must be positioned to receive the signal. The trajectory has to support probe release and orbit insertion. The mission timeline has to protect both atmospheric entry and later orbital science. One elegant science goal becomes several engineering obligations. Once in orbit, the spacecraft faces another challenge. Choosing, Uranus offers atmosphere, rings, magnetic field, gravity. Large moons, small moons, and a plasma environment all compete for attention. Every observation uses time, pointing, power, storage, and downlink. Even a flagship cannot do everything at once, so mission design becomes a kind of ethics of attention. What does the spacecraft watch first? Which moon flyby gets the closest pass? How much time goes to magnetic mapping versus atmospheric imaging, and how much data can the deep space network return from that distance? These become science questions turned operational. Now remember the viewer promise. Uranus remains almost unexplored, not because the next spacecraft needs a better camera. It remains almost unexplored because the real mission must be a system mission. It has to arrive, stop, sample, orbit, tour, store, transmit, survive. So that is why the Uranus orbiter and probe concept is so important. The name sounds simple, but each word carries a scientific function. Uranus is the target. Orbiter means sustained local context. Probe means direct atmospheric truth. Together they answer why another fast pass would be insufficient. And this also explains why the mission is not small. A modest payload can still be highly capable, but the architecture around it is large. Power, propulsion, thermal control, communications, autonomy, probe relay, and operations all have to work in a cold place where repair is impossible. Now, the hard part is that none of this weakens the case. It strengthens it. If the questions were easy, a smaller mission might settle them. The fact that the required measurements demand an orbiter and probe tells us the unknowns are deep enough to justify the ambition. So we arrive at the political sounding part of the story, but we have earned a more careful version. The science community has made Uranus a priority. The mission concept exists. The decadal recommendation is real. The final barrier is that recommended is not the same as launched. Now, arrival looks like the victory moment, but for an orbiter it is the beginning of danger. A flyby can race through the Uranian system and continue into deep space. An orbiter has to give up enough speed for Uranus to capture it. That one difference separates a visit from exploration. Slowing down at the outer planets is expensive because speed has to be paid for somehow. Chemical propulsion is mature and reliable, but propellant is mass. Every kilogram of propellant launched from Earth is a kilogram that cannot be used for instruments, shielding, communications, probe systems, or margin. The spacecraft must carry the cost of stopping for more than a decade before it spends it. Some studies discuss aero capture as an alternative trade-off, using the planet's atmosphere to help brake. The idea is powerful, but it is not magic and should not be treated as the selected answer. Aero capture demands confidence in atmospheric models, heat protection, navigation, timing. At Uranus, where the atmosphere itself is one of the unknowns, that is a serious bargain. Then comes the atmospheric probe. A probe is not a camera dropped casually into clouds. It must separate from the carrier at the right time, enter at the right angle, survive heating and pressure, wake its instruments, measure the atmosphere, relay data before it is lost. The orbiter has to be positioned to hear it. The probe's science is worth the difficulty. Noble gases and isotope ratios carry formation information. Vertical temperature and pressure profiles show atmospheric structure. Composition measurements can test models that remote observations leave uncertain. For a planet whose interior and formation are so poorly constrained, a probe gives a kind of truth no telescope can provide. But probe delivery competes with orbital science. The mission also needs to map gravity, track the magnetic field, observe rings, revisit moons, study the atmosphere over time, return data. A multi-year tour is a choreography of limited fuel, pointing, downlink, power, scientific priority. Think of the spacecraft as a careful accountant. It accounts for momentum, heat, watts, bits, propellant, pointing time, instrument health, and human attention on Earth. Each observation has a cost. Each moon flyby changes the next orbit. Each downlink occupies time. Each heater keeps something alive but spends scarce power. So that is why the mission cannot be described as simply send an orbiter. The word orbiter hides a vast set of decisions. What orbit first? How close to the rings? Which moons receive repeated passes? How much time goes to magnetosphere sampling? How often do we observe the atmosphere? And how much data can return before the next event? A dedicated Uranus mission would have to answer those questions before launch, then revise them after arrival when the planet finally speaks back. Here is the beauty and the burden of orbital exploration. The mission becomes a conversation with the system. Voyager gave us a monologue from a passing spacecraft. An orbiter would create the first real dialogue. But dialogue requires stopping, and stopping at Uranus is one of the expensive verbs in planetary science. Now imagine the arrival after more than a decade of cruise. The spacecraft is finally at Uranus. The planet fills the instruments. The rings and moons are no longer abstractions. At that moment, the mission faces the difference between passing and staying. A flyby can be almost graceful. It follows a path through the system, steals every measurement it can, and lets the planet bend its trajectory onward. An orbiter has to do the opposite. It has to give up enough speed for Uranus to keep it. That usually means a major burn, carefully timed, with propellant carried across the solar system for years for one decisive use. We can hear the engineering pressure in that sentence. Propellant needed at Uranus must be launched from Earth. Propellant launched from Earth increases mass. Increased mass affects the launch vehicle, trajectory, cruise design, instrument budget. Stopping is not a line item. It reaches backward through the whole mission. Aero capture concepts show another possible trade. Use the atmosphere to slow the spacecraft and save propellant. But that asks the vehicle to skim an atmosphere we do not fully know, survive heating, and hit a narrow corridor. It becomes a fascinating idea, not a casual shortcut. The baseline caution remains. Every way of stopping has a cost. The probe adds its own choreography. It must separate before entry, arrive at the right angle, survive heat and pressure, gather data quickly, and relay that data before it is gone. The orbiter must be positioned to listen. The geometry has to work. The timing has to work. A probe is a scientific instrument, but it is also a brief, one-way performance. And after capture, the mission is only beginning. The orbiter must choose how to spend years among atmosphere, rings, magnetosphere, gravity science, and moons. It cannot do everything at once. Exploration becomes a sequence of trade-offs, not a single heroic arrival. Now add the operational rhythm after capture. We would not want the orbiter to spend all its fuel and attention on one beautiful first orbit. We would need a tour that gradually changes perspective. Close passes for gravity, safer arcs for communications, targeted encounters with moons, and periods where the spacecraft simply watches the planet breathe. That tour design is science translated into motion, and every choice leaves something else for later. If we spend a pass on magnetic mapping, we may not spend it on a moon. If we protect data volume for probe relay, another instrument may wait. Staying is powerful because it creates options, but it also forces discipline. Now we need to be precise about Uranus orbiter and probe. The National Academy's decadal survey recommended it as the highest priority new large or flagship planetary mission for the 2023 to 2032 decade. That becomes a major statement from the planetary science community. But it is not the same as NASA approving, fully funding, building, launching the spacecraft. A decadal recommendation is a priority signal. It tells agencies and lawmakers what the scientific community believes should come next. It does not by itself create the mission hardware. This distinction may sound bureaucratic, but for this topic it is central. If we collapse recommendation into launch, we create mission news hype. If we ignore the recommendation, we imply Uranus has no constituency. Both are wrong. The accurate story sits between them. The community has said in effect that Uranus deserves a flagship return. The reasons are strong. Ice giant interiors, atmosphere, magnetosphere, rings, moons, possible model-based ocean layers, exoplanet context. Uranus is not waiting because the science case is weak. It's waiting because a flagship mission is a rare and heavy choice. Flagships can define a generation of planetary work. They need budget lines, formulation, reviews, instruments, launch services, radioisotope power systems, deep space communications, operations teams, years of institutional stamina. Now compare that with the simplicity of the public question, why have we not gone back? Because going back properly is not one decision. It becomes a chain of decisions that must stay aligned long enough for a spacecraft to leave Earth and reach a planet more than a decade later. And the chain has competitors. Planetary science does not contain only Uranus, Mars sample return, Europa, Titan, Venus, lunar science, small bodies, planetary defense, many other priorities all make claims on budgets and people. Opportunity cost is not an excuse. It's how a finite program behaves. We should avoid grievance language here. The story is not that Mars stole Uranus's destiny or that one agency forgot a planet. The more serious point is that outer solar system missions are so large that even top priorities have to pass through timing, money, technology, and portfolio sequencing. Radioisotope power is one example. Deep space missions far from the Sun depend on specialized power systems and, often, scarce plutonium supply. Trade reporting has described this as a constraint in planning discussions. That does not mean the mission is impossible. It means the launch year is connected to industrial capacity on Earth. Budget timing is another. A mission can be scientifically ready before a program can absorb its cost. Formulation may start later than the ideal celestial window. A delay of a few years on Earth can become a different trajectory, a different cruise duration, or a different arrival context at Uranus. Now this is where the answer becomes almost paradoxical. Uranus is still almost unexplored, partly because it is important enough to require the right mission. A cheap repeat flyby would not answer the decadal level questions. The mission that would answer them is large enough to be hard to start. And the decadal recommendation changes the emotional meaning of the absence. The absence no longer means nobody understands the value. It means recognition has not yet become flight. That's frustrating, but it is also a more honest and more interesting boundary. So what would finally change? A real, approved Uranus orbiter and probe would move the planet from the era of one snapshot into the era of residence. It would put instruments in the system for years. It would sample atmosphere directly. It would watch the field, rings and moons as connected parts. Until then, the archive remains lopsided. Voyager supplies the only local close-up truth. Telescopes supply the long-distance timeline. Models connect the pieces. Reanalysis extracts more from old measurements. All of that is science. None of it is the same as being there again. Now we can answer the original question without shrinking it. Uranus is not almost unexplored because the solar system forgot it. Uranus is almost unexplored because the first visit was a flyby, and the next meaningful step is one of planetary science's most demanding missions. And that answer points beyond Uranus. Distance decides what remains partly known. The farther we go, the more exploration becomes a negotiation between curiosity and machinery. Uranus is the cleanest case because the contradiction is visible. One major planet, one close look, and decades waiting for the mission that can finally stay. Now we can talk about the Uranus orbiter and probe without turning it into mission news hype. The Decadal Survey recommendation is real and important. The National Academies placed UOP as the highest priority new large or flagship class planetary mission recommendation for the 2023 to 2032 decade. That's not a casual endorsement. It means the scientific community looked across major planetary priorities and concluded that an orbiter and atmospheric probe at Uranus would answer questions of exceptional value. Interior structure, atmosphere, rings, moons, magnetosphere, formation, ice giant context all converge on one mission architecture. The recommendation says Uranus is not forgotten. It says the opposite, but a decadal recommendation is not a launch. It becomes a priority signal, a strategic guide, and a powerful argument for what should come next. Formal mission approval, funding, formulation, hardware construction, launch vehicle commitment, radioisotope power allocation, and operations planning are separate steps. This distinction protects the viewer from a common misunderstanding. When people hear about a recommended mission, it can sound as if the spacecraft is already waiting in a clean room. For UOP, the safe status is more careful. A recommended flagship mission concept, not an approved and funded flight project, unless formal decisions change. Flagship missions are rare because they reshape a planetary program. They can cost billions. They require specialized teams, long design periods, launch commitments, deep space power systems, decades from concept to arrival. Choosing one often means delaying or reshaping others. That's not a scandal. It becomes the nature of missions big enough to answer the hardest questions. Uranus also competes with the rest of the solar system in a practical sense. Mars missions, lunar programs, asteroid missions, Europa, Titan, planetary defense, telescopes, and technology development all live inside the broader space science ecosystem. Each has advocates, each has scientific value, each uses money, engineering labor, launchers, attention. So the question is not whether Uranus deserves a mission. The decadal process has already made a strong case that it does. The question is how a priority becomes metal, software, fuel, instruments, a launch. That transformation is slow because a flagship cannot be wished into existence by a good white paper. And trade reporting has also pointed to radioisotope power availability and budget timing as possible constraints. We should treat those reports with attribution and caution, but they fit the larger pattern. A mission to Uranus needs more than a trajectory. It needs the right power system at the right time, and that power system comes from a limited production and allocation pipeline. This becomes where the answer becomes mature. Uranus is not still almost unexplored because it failed to be interesting. It's still almost unexplored because interest had to become priority. Priority has to become approval. Approval has to become hardware. And hardware has to survive a long route to a distant planet. And until that chain completes, the decadal recommendation sits in a strange emotional place. It's hopeful because the scientific case is recognized. It's frustrating because recognition is not arrival. It becomes the difference between drawing the bridge and standing on the far side. Now separate desire from commitment. The decadal survey matters because it is the planetary science community saying, in effect, this is the next great large mission we should pursue. That isn't a press rumor. It isn't a casual wish list. The formal priority setting process gave UOP extraordinary weight. But a decadal priority still has to become a flight project. That means formulation, budgets, reviews, instruments, partners, launch planning, power system availability, workforce, and years of institutional decisions all sit between recommendation and launch. A recommendation can point the arrow. It does not build the spacecraft by itself. We should resist the cheap version of the story. It would be easy to say Uranus remains unexplored because someone failed to care. The evidence does not support that. Scientists have argued for Uranus precisely because the questions are important. The problem is that a flagship mission is not a single purchase. A flagship is a long commitment that reshapes a whole program around it, and those programs already carry other promises. Mars sample return questions, Europa and outer planet missions, lunar work, small missions, telescope priorities, planetary defense, operations for spacecraft already flying all live in the same broad ecosystem of money, people, launch services, political attention. We do not need to rank them melodramatically. We only need to see that one flagship can crowd the calendar for years. Radioisotope power makes the story even more concrete. Outer planet missions need reliable power and heat far from the sun. Trade reporting has highlighted plutonium and RTG availability as one constraint on ideal early schedules. That does not mean UOP is impossible. It means the mission sits inside a supply chain as real as the trajectory. So recommended is not launched because planetary exploration has stages. First, the science case becomes clear. Then the community ranks it. Then agencies and governments decide when and how to fund it. Then engineers turn the concept into hardware. Uranus appears to be somewhere in that long middle distance, scientifically compelling, formally prioritized, and still waiting for the commitment that turns priority into a spacecraft. And we can see why that matters. We need the next constraint. Here's where we slow down. Imagine we are following the evidence. Look at what we have learned. We can place the next piece. So we keep the scale in view. Think of the system this way. Uranus remains difficult because every answer is tied to a measurement we barely have. We know the axis is strange. We know the magnetic field is tilted and displaced. We know the flyby was brief, but we do not yet know how those clues fit into one history. The honest position is not that Uranus is mysterious in a decorative sense. The honest position is that the planet still has too few close measurements for the question it asks. Each missing pass leaves a gap between shape, season, interior, magnetism. That gap is why one more mission would not be a luxury. It would be the first real test of whether our picture of ice giants is built on a sample of one encounter. Now we can hold the Uranus problem in a clearer form. The planet is not unexplored because it lacks interest. It's unexplored because distance turns every useful measurement into a mission design problem. We need time in orbit. We need repeated views. We need the field and the moons and the rings measured together. So the missing answer is practical as much as scientific. A flyby can reveal a contradiction. Only a dedicated mission can test what the contradiction means. Now we can hold the Uranus problem in a clearer form. The planet is not unexplored because it lacks interest. It's unexplored because distance turns every useful measurement into a mission design problem. We need time in orbit. We need repeated views. We need the field and the moons and the rings measured together. So the missing answer is practical as much as scientific. A flyby can reveal a contradiction. Only a dedicated mission can test what the contradiction means. Now we can hold the Uranus problem in a clearer form. The planet is not unexplored because it lacks interest. It's unexplored because distance turns every useful measurement into a mission design problem. We need time in orbit. We need repeated views. We need the field and the moons and the rings measured together. So the missing answer is practical as much as scientific. A flyby can reveal a contradiction. Only a dedicated mission can test what the contradiction means. Now we can hold the Uranus problem in a clearer form. The planet is not unexplored because it lacks interest. It's unexplored because distance turns every useful measurement into a mission design problem. We need time in orbit. We need repeated views. We need the field and the moons and the rings measured together. So the missing answer is practical as much as scientific. A flyby can reveal a contradiction. Only a dedicated mission can test what the contradiction means. Now we can hold the whole answer in one place. Uranus is still almost unexplored because humanity has only done the first kind of exploration there. Voyager 2 gave us reconnaissance in January 1986. It flew past once, close enough to discover rings, moons, winds, and a strange magnetic field too quickly to turn the Uranian system into a fully measured world. That encounter was historic. It should not be minimized. Without Voyager, we would know far less. A flyby is not an orbiter. It isn't an atmospheric probe. It isn't a multi-year tour of a planet. It's rings and its moons. The difference between those mission types is the difference between seeing a door and walking through it. So the title question has a serious answer. Uranus remains almost unexplored because the measurements that matter now are difficult measurements. Deep atmospheric composition, noble gases and isotopes, gravity and magnetic mapping, seasonal monitoring, ring and moon dynamics, possible model-based ocean tests, and the interior structure of an ice giant that gives off surprisingly little heat. The mission that could answer those questions has to pay a high price. It must travel to a world about 19 astronomical units from the Sun. It must operate where sunlight is weak, communication is delayed, and heat is scarce. It must launch in useful geometry, survive a long cruise, arrive with enough capability to stop, deliver a probe, return data from a system no spacecraft has entered since 1986. Uranus orbiter and probe matters because it names the right next step. The Decadal survey recommendation tells us the science community sees the value clearly. A recommendation is not a launched spacecraft. The gap between those two things is made of budgets, power systems, launch windows, workforce, risk, the long patience required by outer planet exploration. By the end of this video, the misleading part of the phrase, "we already visited Uranus," should be clear. Yes, we did once, that one visit opened the subject rather than closing it. What would finally change is not just the sharpness of the pictures. A dedicated orbiter and probe would change the class of knowledge. Uranus would stop being a planet mostly inferred from one flyby and remote watching. It would become a system measured from within, that is the quiet lesson Uranus gives us. Even inside our own solar system, distance still decides what we know directly and what we only piece together from traces. If this question leads anywhere next, it leads outward, to Neptune, to the edge of the solar system, and to every place where a world can be named, mapped from afar, still partly unknown. Now the answer can be held in one hand. We still know Uranus mostly through reconnaissance, not residence. Voyager 2 opened the door in January 1986, looked through it with precision and kept moving. What Uranus needs next is not another brief glance. It needs residence. A dedicated orbiter and atmospheric probe would change the evidence itself. The orbiter would map gravity and magnetism repeatedly. It would watch seasons and storms. It would study rings as moving structures instead of dark lines. It would revisit moons whose surfaces may record heat, stress, and possibly model inferred ocean layers. The probe would descend into the atmosphere and measure composition directly. That would not make Uranus simple. Good exploration rarely makes a world simple. The next natural question is what a single dedicated Uranus mission would have to measure before the planet stops being a silhouette.